Okay, hello again and welcome to another version of Algebra 2 Notes with Miss Faust. Today we're starting with a big theorem that's used a lot in algebra. So I'm going to explain the theorem. You probably will want to pause and write some of this down. And then we'll do some examples. And it's one of those, like any theorem, that when you just see the words, it's a little bit confusing, but once we do some examples, you'll start to see that it's really not that hard at all. And this just adds another layer on top of the factoring that we've been doing, and when you get back to class, you'll see how it all starts to tie together. So this is lesson 4.7.1. Our essential question is, how do you find the rational roots of a polynomial equation? And rational roots also will show us what the factors are. So remember that when we're looking at these, when we're looking at big polynomials, our goal for a long time has been to get them into factored form. And this is just another layer of how we do that, how we get from this multiplied out standard form back into factored form. So the first thing to know is that this p of x just represents any polynomial. So I've written it with variables here just so that you know that it applies to absolutely any polynomial. These a's would all be numbers, as would the b. The difference between them is the a's are the numbers with the powers of x, and the b is the number by itself at the end. The leading coefficient is the one that goes with this highest exponent here, so this x to the n. That just means that n is the highest exponent in the whole problem. And thinking about that now, yeah. So x to the n represents the highest exponent, and this a is going to be really important. This we're going to look at again and again, as we are this b. So those are the two things that really to pull out from this example. So that brings us to the actual rational root theorem, which let me just adjust this a little so you can see the whole thing at once. Working on the contrast today. I'm not sure why it's being a little bit annoying, but we'll take what we can get. Okay, so the rational root theorem states let p of x be a polynomial with leading coefficient a and constant b. And we just talked a little bit about what that leading coefficient and constant look like in the polynomial. So you're going to want to find those first. N, so we're going to use an n, and that's going to represent any factor of a. So any number that multiplies to give you a. That's what n is. M represents any factor of b. So you, like if b is 9, the factors of 9 would be 1 and 9 and 3. So that would be, m could be any of those numbers. All the possible roots or factors of p of x, that was our original polynomial, are all of the combinations of values of m divided by n. So we want to look at the combinations, not just the individual numbers. So we're going to take all of those possible m's and all of those possible n's, we're going to divide them, and that'll give us all our possible roots. And then this is the big important part, the rational roots, or the factors. I like to just add that in because sometimes we forget that that's really what that means. Of p of x are the values such that p of x divides by m over n with no remainder. So that means when we do that synthetic division, we get a remainder of 0. So basically what we're going to do when we look at these is we're going to do a little bit of division with numbers, and then we're going to do a whole bunch of synthetic division. That's the plugging in, the quick way of doing the division of these. So like I said, it sounds complicated here, but as we start doing it with some problems, I promise you it will become clear. So let's go ahead and start looking at some examples. So in our first example, we're trying to find all possible roots of p of x equals 2x to the fourth plus x to the third minus 19x squared minus 9x plus 9. All possible roots, remember, mean just the possible ones. So we're just going to sort of use the first part of that formula. So what we want to start by thinking about again is what our leading coefficient is and what our constant is. So this is our leading coefficient, and this 9 is our constant. So what we need to do is we need to find all possible values of n, and those are going to be all the factors of the leading coefficient. So if we think about that, the factors of 2 in this case. So the factors of 2, well, multiplication problems you can do to get 2 are 1 times 2 And you can also do -1 times -2. So what we do is we just put a plus or minus in front of both of those, and that way we have all possible combinations. So plus or minus 1 and plus or minus 2. M are the factors of the constant term, which in this problem is 9. So our M values, think about factors of 9, well, plus or minus 1, plus or minus 9, because 1 times 9 and -1 times -9, or plus or minus 3. 3 times 3 is 9, -3 times -3 is also 9. So those are our M and N. And then the possible roots, which is all we're looking for here. So the possible roots are given by M divided by, the possible roots are given by M divided by N. So what we want to do is we want to take all of our M's and, all of our M's and divide them by all of our N's. So what I like to do when I do this is I just start with one of my M's. So one of my M's is plus or minus 1, and I divide that by all of my N's. So plus or minus 1 over plus or minus 1, plus or minus 1 over plus or minus 2. And as long as you're systematic about it, you won't lose track of any of them. Plus or minus 9 over plus or minus 1, plus or minus 9 over plus or minus 2, and plus or minus 3 over plus or minus 1, and plus or minus 3 over plus or minus 2. Okay, so we can make that look a little bit neater because 1 divided by 1 is just 1, so that really gives us plus or minus 1. 1 divided by 2, whether they're positive or negative, gives us plus or minus 1/2. 9 divided by 1 is plus or minus 9. 9 divided by 2, we only need 1 plus or minus. 3 divided by 1 is plus or minus 3, and 3 divided by 2 is plus or minus 3 over 2. So those are all the possible roots. We're just taking all the factors and putting together all the different combinations of ways that we could combine those factors. So let's do another example, and this time we're going to actually figure out if some things are roots. So this time we're going to find the possible roots of p of x equals x cubed plus x squared minus 8x minus 12. And then we're going to check and see if x equals positive 3 is a root, and if x equals -2 is a root. Okay, so let's think of that like an A, a B, and a C. So for part A, all possible roots, I think about my polynomial. So my p of x was x to the third plus x squared minus 8x minus 12. So to think about all of my possible roots, I think about this leading coefficient, which is 1, and I think about this constant, which is 12. So my n's are my factors of 1, which is just plus or minus 1. My m's are my factors of -12. So plus or minus 1 and plus or minus 12, because 1 times 12 is 12. Plus or minus 2 and plus or minus 6. And plus or minus 3. And plus or minus 4. Now at this point, to list all the possible roots, I have to do m divided by n. But notice n is just 1. So all of those divided by 1 just give you the same exact list. So plus or minus 1, 12, 2, 6, 3, and 4. So now I need to check and see if those two numbers that we were given are actually roots. So if I think about 3, first I look and I see if 3 is on this list. 3 is on the list, so it could be. So in order to figure out, is 3 a root? I do synthetic division. I put the 3 over here. I go back to my problem. I use my coefficients, 1, 1, -8, -12. Bring down the 1, 3 times 1 is 3. 1 plus 3 is 4. 3 times 4 is 12. Negative 8 and 12 is 4. 3 times 4 is 12. Negative 12 and 12 is 0. Because that's a 0, that means, yes, it is a root. Okay, if this hadn't been 0, 3 would not be a root. Part C, again, is negative 2 a root? Well, we look first and see if it's on the list. And we see negative 2 is on the list right here. So we do the synthetic division again. Negative 2, 1, 1, negative 8, negative 12. Bring down the 1. Negative 2 times 1 is negative 2. 1 plus negative 2 is negative 1. Negative 2 times negative 1 is 2. Negative 8 plus 2 is negative 6. Negative 2 times negative 6 is 12. Again, we get a 0. So again, we know that negative 2 is a root. Again, if we'd gotten something besides 0, wouldn't be a root. But because we did get 0, we know it's a root. So we know 2 of the roots for this problem are 3 and negative 2. That's going to be really helpful when we go to write the final factored form, which is what we'll learn about next time. For right now, we're going to work on figuring out if things are roots. The other thing just to know and remember is that this number is the most number of roots you can get, whatever that highest exponent is. So this one could have one more root. We know 2 of them already. So in order to find all 3, we actually don't have to go through every single one of these possibilities. And we'll look more at that next time. Okay, so the last thing that we're going to do today is we're going to look at how this idea helps us factor something completely. So get all the way from the factored form to the standard form. So again, what you want to do when you're asked to factor a polynomial completely is you want to find the possible roots. So let's find the possible roots for this. Again, we think about our m and our n and our a and our b. So our a is 1. Our b in this is negative 60. That's our b. A equals 1. So our n, remember, is the factors of a, plus or minus 1. Well, that's kind of nice because that's going to be an easy one again. And our m, now we have negative 60. So this is going to have quite a list because 60 has a lot of factors. Plus or minus 1, plus or minus 60, plus or minus 2, 30, 3, 20, 4, 15, 5, 12, 6, and 10. Now I did that quickly because this is what I do. Obviously it might take you some more time to find all the possible multiplication problems that give you 60, but remember, you're really just looking for multiplication problems that give you 60. That's the idea here. So down here, instead of listing all of these again, I'm just going to write that m over n is equal to m in this case, because all our n's are 1, so it's just all those divided by 1. So in order to factor it, what I have to do next is I have to find one root. So you can try a lot of these. If you're working on this in class with other people around, you sort of split them up and everybody tries one. The one that we're going to try for right now, though, is x equals 5. Okay? So x equals 5 is going to work. Just so you know, if it didn't work, you would just try another one. Trial and error, like we've been doing with factoring. So we're going to try 5. So we put 5 on the outside. And 5 again is on this list. That's how I chose 5. I do my synthetic division. So 1, 2, negative 23, and negative 60. I leave a space. I bring down the 1. I get a 5. I get a 7. 35. 35 minus 23. My brain is not working. 12. 5 times 12 is 60. Give me a 0. This actually tells me two things. This tells me x equals 5 is a root, which means x minus 5 is a factor. The other thing this tells me is that this original polynomial divided by this, remember, is equal to this. So x cubed plus 2x squared minus 23x minus 60 equals x minus 5 times, remember writing factored forms, 1x squared plus 7x plus 12. Well, now, by finding one root, I can get the entire factored form. Because I look at this, I think about two things that multiply to 12 and add to 7. Two things that multiply to 12 and add to 7 are 4 and 3. So my fully factored form is x minus 5 times x plus 4 times x plus 3. Okay, we'll be working a lot more on this in class. I just wanted you to start seeing this. So in the next couple of days, that's why we spent so much time factoring, because that last step, you always want to factor this way after you've done some synthetic division, and then this gives you all the possible roots. Any questions? Write them right over here in the margin, or right down here at the end, and we will see you again soon in class. Thank you for your attention, and have a wonderful day.